Okay, so let's start the lecture. So today we will consider the supersymmetric QCD in for the n equal 1 space. So this is something typical example we can analyze exactly in a supersymmetric field theory in various dimensions, various matter contents. Probably this is the simplest or most interesting one. N equal 1 super QCD and n equal 2 super Anomaly theory. And maybe it's a 4D case. Of course, this is a old subject, and there is a famous review on that. But okay. What I will talk about is a very, some basic topics in a huge, huge arena of such a subject. Okay. So let's consider super QCD with the gauge group G equals SUNC. And NF flavors. Okay. That means superfield we will consider is first order vector multiplet for this SUNC group. So it's a joint representation of SUNC. And QI, Q tilde I. This is these two are chiral superfield, so which couple to this vector field, and this is a fundamental representation of a gauge group, and this Q tilde is an anti-fundamental representation of the gauge group. But still, this is a chiral superfield, so we should distinguish Q tilde and Q dagger. Q dagger is an anti-chiral superfield, and it's a representation. It's a NC bar, that's anti-fundamental representation of gauge group, but it's different from Q tilde. So there's a Q dagger, Q tilde, and Q dagger. Okay, and this I is labels for the flavors. So 1 to NF. Okay. The action we will consider is use this is what I have shown yesterday. This is a kinetic term for the gauge multiplet, and this is a kinetic term for the chiral multiplet. Here, V is a representation of this Q, and this is so this V and this V is in some sense different. V is a representation of fundamental representation. Here, it's an anti-fundamental representation. I denote this as the same matrix, but same V, but it's different. And we can at the master sorry, more precisely this there is a Hamilton conjugate for this. Okay. So this is a superpotential. So actually, for this model, renormalizable part of the renormalizable action is only this one. We can only add the mass term. We cannot introduce yeah. And okay. The modular space of vacuum is parameterized by gauge invariant chiral superfield. That is Mason and the barrier. So R1, this R, NC. Epsilon. Okay. Okay. These yeah, Q is fundamental and Q tilde is sorry, anti-fundamental. So this is we can construct a gauge invariant like user method. But user method is like Q dagger, but here you use a Q and Q tilde. Then this M is a chiral superfield. So this is a gauge invariant combination of the chiral superfield. And if NF is equal or greater than NC, we can construct something like a baryon. This is these gauge indices R1 to RNCs are contacted by epsilon tensor. So this is the singlet of the gauge group. It's like a baryon, but actually it's not like a real baryon, but it's called baryon nickel plate. And from the Q tilde also we can construct such things contacting these NC indices by epsilon tensor. Okay, so these are the only gauge invariant chiral superfield. So these are the moduli. So these should be the moduli of the vacuum for this theory. Okay. Okay. Of course, there is a Q dagger is also a gauge invariant superfield, but it's not a chiral, so we can forget about it. Okay. And there is some comments. So these meson and baryons are not independent. Okay. Okay, so this is yeah. Okay, yeah. You can check this relation from this definition. Okay, this is just some property of the SNCD algebra. Okay. Anyway, and beta function for this model is computed as usual. And okay, so the perturbative beta function becomes okay. And lambda, we define lambda such that okay, this, yeah, and as I explained, this is exact. This value of beta function is exact because of the holomorphy. Okay. So now we will use a technique to determine the effective superpotential. So in order to do that, we need to first consider the symmetry of the theory. So there is a 3U1 symmetry. Sorry, this plus. Okay. So there's a 3U1 symmetry. First one, this X is a U1R. Sorry, here symmetry means we will assign the charge for the coupling constant also, like m or tau or something like that. So this is yeah, this is not a symmetry of the usual sense, but here because it's symmetry. But here this one is R charge. Okay. And this one, these are user charge. This is called a baryon or U1 vector. This is a U1 actual, like that. But it's, yeah, it's a bit different. Anyway, Yeah, this definition of the U1B is Q and Q tilde opposite sign, and U1A is the same sign. Okay. So this U1B, yeah, sorry. So this meson is invariant under this U1B. Okay. A, B, this one, U1 X. Huh? Sorry, this is a plus and this minus. So the opposite. It's a plus, 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 plus. Okay? Okay. Sorry. Yeah, if you cannot see, yeah, please ask. Okay. But, okay. As yesterday's talk, these can have anomaly. Okay. Actually, this U1X and U1A has anomaly. This U1B is not anomalous because of there is a different charge, opposite charge, so anomaly are cancelled. But these two have an anomaly. But if we consider this combination, then, so this U1R is non-anomalous. Okay. So this combination is determined by, actually there is a this maybe we should use. Okay. This U1 this R symmetry rotate the fermion in a gauge multiplet. Okay. And also this rotate fermion in this chiral multiplet. That gives this NF and NC. NF is anomaly from this chiral multiplet, and NC is come from gauge multiplet. And but this NF is comes from this one. U1A only rotates the chiral multiplet. There is a NF multiplet, so it's NF. So if we consider NF times JX times NF minus NC, then it's cancelled. Anomaly cancelled. So this is non-anomalous one. And for the U1A, this is anomalous, but here we consider this one. So this is a exponential I theta minus e squared 8 pi squared. Okay. Then, if we change the theta to theta plus something, then this generates something like there is these terms. This gives us something like alpha f at f. Sorry, there is some coefficient here. Okay, and this U1R means psi or something like that. It gives some phases. It's oh my gosh, oh my god. Oh, sorry. Exponential. Yes. Okay, this is a anomalous. Sorry. This anomaly means if we change the measure, path integral measure, then it gives some terms proportional to the instant on charge. Okay. So if we think theta is also changed some amount, then we can cancel these terms. Okay. And then we think this U1A is in the same symmetry. I mean, if we change the coupling constant also, then this U1A also becomes like a symmetry. And the combination is this one. This one is like exponential. This one is proportional to exponential I theta to NF I alpha. By this combination, okay, if we assign theta or lambda to this charge, then this U1A is also like a symmetry of the theory. Okay, so we can use this U1A as a can be as a selection rule. Okay. Then okay, so this type of we can use it in this type of argument for any theory, 3D, 2D. If there is an anomaly, then we can use that. Okay. So then charge for these fields and coupling constant is like NF 1 NF minus NC over NF. Okay. So this is a fundamental of NF. NFL and sorry here, NFL and NFR is NFL only rotate Q. NFR only rotate Q tilde. Maybe you think this is not the symmetry of the theory, but if we assign mass as a NF bar mass as a discharge, then the theory is invariant under that. If with the mass, then the in a symmetry as a usual sense is a diagonal part of this SENF times SENF. But here we split it and we assign mass to the some flavor charge. Okay. Okay. Then this, with this with this charge, like this mass term is invariant, and this okay. Of course, for massless case, this SENF L and R are symmetry of the theory. And okay, so U1A is this one, so it's charge 1, and U1R is a combination of U1R and U1 is U1X and U1A. So this one, because of these things. Sorry, yes, yeah. Symmetry means okay, yes, yeah. So Yes. Yeah. So there is a U1X, U1X, VA. So, but instead of X, we use this combination. So there's only 3. Yeah. So yeah, yeah. U1X is a bit. Yeah. We have this non-anomalous combination. But this U1A is still anomalous, but we have 3 independent charge. Sorry, which one? Sorry, could you spell? This one. Why? This terms contains a theta term here. If we change theta, like this one, that means rotate lambda as like this one. And this gives this, theta, I mean, in action contain this theta term here. So this shift gives these terms additional. But U1R was anomalous charge, anomalous U1 symmetry gives such a instant on charge as from first integral measure. Then it can be cancelled. So then it becomes a symmetry of the cell. Okay. Maybe, yes. Yeah, we assign the charge for these two parameter, two coupling constant as action becomes invariant under these. Oh, sorry, M is, yeah, M is over. Or NF. Oh, it's not good. It's not good. Something. Yeah. Something. So this is a 2 times this one or something like that. But anyway. Okay. Star, yeah, sorry. Star is we should assign the charge for M as this combination is invariant. Okay, and okay. Yeah, it's sorry. So I think it should be a 2 minus NF over NF minus NC. 2 or something like that. Then these two are cancelled, and then U1R charge becomes 2. Then yeah, it's okay. But yeah, so sorry, I'm not so sure. I think this is correct. But capital M. This is a meson. Capital M is a meson. So it's a Q. Sorry, Q. Right. It's like that. Okay. Okay, sorry. So the meson is this one. As I. So meson is QQ tilde. So it's a NF. This one is a singlet, but this one is a charge. So it's a completely different notion. Anyway, yeah. This is yeah. Okay. And this, so this is charge 2, this charge 0, this charge is NF over 2 NF minus NC. Okay, I think this is correct, but yeah. Then, effective potential. Integrating out all fields and including all quantum correction, including a non-perturbative effect, should respect these symmetry. Okay. Then only the combination is this type. Without mass. Without mass, this is only the one unique invariant combination of these charges. So this is a QQ chilled, maybe QQ chilled. This is it. Okay. At least you can see this combination is invariant under these assigning the charge. Okay. Of course, this is determinant, so this is CN flavor charge cancelled. I cancelled or becomes singlet, and this U1A charges. This is 2, but this is determinant, so 2. This have 2 NF charges, so it's cancelled by this 2 NF here, and also U1 for the U1R. You can see this factor cancel this one, and there's a NF, so NF also cancelled. We have a 2, and superpotential should have a charge R charge 2 because of this rotation, because of D squared theta. So because of this rotation and this one, the superpotential should charge 2. That is a basic notion. Okay, sorry. Okay. Okay. So this super QCD, if you compute everything in a lattice, numerical simulation, everything, then you should find non-perturbative coefficient should be this one. This is correspond proportion to lambda. This here, so this should be some non-perturbative correction, because perturbative correction should be a log of lambda inverse or something like that to get this 1 over squared. Okay, perturbative coefficient should be the expansion by g squared. So it's a very strange things from this dynamical scale lambda. Okay. Sorry. Sorry. Non-normalization. Yes. Yeah. It's the same as like West Seminole model case. Because of this tau dependence or something, we need to this combination. And then a part of the equation cannot be allowed for the effective potential, because this has a natural charge. I mean, this combination has a natural charge. So this g squared is not good variable, and it's cannot appear in effective potential. Okay, and this is and also there is this factor. So this is not an instant expansion. Instant expansion should be this should be expansion of this combination. But there is some fractional power. So this except NC equal NF plus 1 case, this is not an instant effect. It's not something strong coupling effect, but we don't know what it is. But it should be this combination. That is a consequence of the holomorphy. Okay. And including M, there's some we need some limit, some analysis using M goes to 0 limit and M goes to infinity limit or something like that. But then we can find, including M, this is only the allowed combination. Okay. Okay, usually, yeah, we should compute the coefficient here, and we should confirm this is non-zero, but actually it's non-zero. We can compute it from the some point there, but Okay. Mm-hmm. Any space-time, yeah, any space-time engine. This, you mean this type of the argument, or holomorphy, or something like that? Yeah, actually, yeah, at least a similar argument can be applied. If some quantity is holomorphic, and then a holomorphic, and we can assign some charges for the coupling constant also, then we can apply such, apply this procedure to anything. Yeah. Especially 3D n equal 2 case or 2D 2 comma 2 case is almost same as this type of argument. Okay, then this gives, sorry. Okay. NC equal NF. It's okay. It's just one. So sorry. NC equal NF is this one. Singular. Yes, yeah. Okay, sorry. Sorry. This, yeah. Sorry. I'm sorry. Thank you. This should be NC is less than NF. Sorry, I used this one. Because we forget about the baryon. Baryon exists for NF, NC is greater than NF. That case, we can construct other terms. So sorry, I'm sorry. And NC is larger than or equal to NF case. We will explain it later. But here, that is this is for the this case. Sorry, without barrier. So this determinant is determinant for the flavor indices. Okay, so this is a meson. So gauge indices are already contracted, and it's gauge invariant operator. Okay, so this also for the flavor indices. Okay, so if we integrating out this meson from this effective superpotential, this gives a quantum vacuum. Okay, quantum vacuum. So then, this is a condition for this F term. I mean, flatness condition of this superpotential. Then this shows we can compute. Yeah, now we computed this correlation VB of the theory exactly like this one. Okay, and there is this fractional factor. So there is a NC back here because of the we have a choice for the root of 1 over NC or something like that. Okay. So this is consistent with the Witte index. I will explain later, but okay. Okay, so this is this is an exact result for super QCD using holomorphy. For this NC is less than NF. And for NC NF flavors. This and sorry, massless case. This is a famous diagram or something like that. Yeah. NC vacuum? Okay, for this model. Yeah, there's a 1 over NC, so equal can be omega 1 or omega 0, omega 1, omega 2 dot omega NC minus 1, and omega is exponential 2 pi I over NC. Okay, so if there is this factor, there is ambiguity for solving this one. Yeah, and there is a NC types of ambiguity. So, yeah, there's a phase ambiguity, NC phase ambiguity like this type. Yeah, so there's NC vacuum. Sorry, confinement, no vacuum? No. Sorry, I will explain. Sorry. Yeah. Okay. So this means, first of all, this theory here we consider the m equals 0 case, massless case, and we will call this as electric theory. Electric theory for some reason. Okay. So this means first of all, free electric. This is because this case here NF is greater than N3 NC, and beta function is so then beta function is positive for this case. Okay. Positive, negative. Sorry, it's yeah, it's positive. Sorry, it's positive. So it's non-asymptotic free. It's non-asymptotic free means asymptotic free means in a UV it's a free theory. Non-asymptotic free means in IR it's free. So actually this theory is not defined, very defined field theory because it's non-asymptotic free. But yeah, if we define it as a cutoff theory, then infrared theory will be a free theory of Z equal SUNC. Okay, so there is a free gluons or something like that. So it's called free electric, and at NF equals 3 NC. Then beta equals 0. And at least perturbatively, beta function is this beta function exact. So it's exactly 0. That means the theory is a super conformer. So here, the theory is a super conformer. It's a super conformal field theory. And it should be non-trivial. Not a trivial superconformal field theory. This is very special for supersymmetric theory because in usual gauge theory, beta function have many things. So it's very difficult to find where beta can be 0 or something like that. But here, for n equal 1 supersymmetric QCD case, there's only one parameter. It's a one loop beta function. So tuning the flavor symmetry or some choosing some matter content, we can make theory becomes super conformal. Okay. And actually, before this work, our Cyber's work, there is no known probably 4D non-trivial super conformal field theory. So this is the first example of the non-trivial super conformal theory in 4D. Okay. And I'll explain. And actually, I will explain what's this one. This region is a conformal window, and we will show. Yeah, there's a claim. There is Seiberg dual. It's called magnetic dual. I will explain. And this phase is just magnetic dual becomes IR free theory. And then it's called free magnetic, like this free electric theory. And here, it's is a Higgs phase. I will explain. And this phase has no vacuum. And if NF equals 0, it's a confinement. Sorry, no. Sorry, NC vacuum. Sorry. Here, sorry, there's no vacuum. Here, it's sorry. Yeah, it's this this behavior can be seen from this one. By taking m goes to 0 limit, then because of the this factor, and there's a 1 over nc and determinant m, so this fact here, it goes like nf over nc. Because of this is determinant, there's 1 over nc, so it's like that. So this is 1 over m. So this region, this nf is less than nc case. This is this is less than 1. So this becomes infinite by taking m goes to 0. So in the massless limit, this VB becomes infinite. It's called runaway behavior. Okay. Actually, there is no solution for this superpotential without mass term. It's called runaway type. So infinity of the this meson space is a vacuum. So then we say there is no vacuum here. And for the nf equals 0 case, nf equals 0 case is a limit of this what's 0 and nf equals 0 or something like that. It's same as this structure. So there we have a NC vacuum. Okay. Okay. So then, so this is a result of the n equal 1 super QCD. But so I will explain what's a Seiberg dual or Seiberg duality. Seiberg dual. So this is a conjecture in a string theory, or almost all claim is a conjecture. But this we believe, almost everyone believes this is true, but it's a conjecture. Anyway, it states there is a theory called the magnetic dual. Magnetic theory. Okay. The electric theory is superconformal at nf equals 3 nc. And the conjecture is there is some theory which which is different from this theory, but which flow in an infrared into this superconformal field theory. So it's like that. UV infrared. It's a superconformal field theory. Like this one. This superconformal theory is this one. And the magnetic dual is so magnetic dual is this magnetic theory is this theory. First of all, gauge group is different. So it's like a super QCD, but there is an extra gauge singlet. Sorry, NF. So I think this NF. And good. Okay. So this is a magnetic theory. Okay.
What about the massless theory, which tells you that it's an electric theory rather than a magnetic? If there is a duality, why do we call the original one a free electric theory and the second one a free magnetic?
Sorry. I called this theory, this super QCD, as an electric theory. Electric. Why? Okay. So it's like a electric magnetic duality in U1 gauge, abelian gauge theory. So it's a yeah.
Like for Maxwell's theory, I call it an electromagnetic theory.
Right. Why? Yeah. Okay. It's just a name. Yeah, just a name. So maybe you can forget about the meaning of this name. This is just called electric, and this is just called magnetic. And actually, it's like a strong weak duality or something like that.
So there's two theories being linked by a duality which swaps. How much greater is that? Theories are the same theory?
No. I will explain. What is the Seiberg? What's the meaning of the Seiberg dual, and what is the meaning of the magnetic theory is dual to Seiberg. Actually, as explained here, in a user duality, electric magnetic duality in the abelian case, or Ising model to the Ising model, or massive Tilling and the Zine-Gordon case, or n equal 4 super symmetric case in 4D, there is a duality. That is equivalence. Okay, the two theories are completely equivalent. That is the user meaning of the dual theory. The theory is look like different, but physical content is same. We can map the correlator, state, everything to between the two theories. Here, this magnetic dual is not like that. If the two theories are same, then it's a same point in this is a space of the theories in RG flow. So if two theories are same, then it should be a same fixed point or same flow. But the claim is that this magnetic theory is a different theory as this electric super QCD. But in the infrared limit, it's same. That is a claim. Okay, so it's different from the user. What is the user? We can use duality for many things, but it's not. Yeah. Yes. Actually, this case is UV theory is in a already fixed point, but in general, some two different UV theory have same IR fixed point, and especially if this IR fixed point is a non-trivial supercommonwealth theory, we say it's a Seiberg dual, at least in 4D n equal 1 case. It's there are many names, mirror symmetry in 3D. It's an S-duality or something like that. But this duality. Here the Seiberg dual means two theories have the same infrared limit. Okay. Okay. Under this case, magnetic dual, yeah, actually, infrared limit is trivial, I mean free theory. But here, infrared limit is non-trivial conformal field theory. Okay, it's called the conformal window for the n-1 superconformal field theory. Okay. Okay. Oh. Okay, so there's some comment. So these two theories have different gauge groups. Okay, it's a typical in duality. So in a user sense, or in a user textbook in the field theory, gauge group is essential. Gauge symmetry is essential for defining the theory. But here, the two theories with the different gauge groups should be same, at least at the infrared. So then actually the gauge symmetry is just a redundancy of the theory. Gauge symmetry does not fix the theory. Okay, so different gauge theory, different gauge theory with different gauge group can have same physical content. Okay, but global symmetry is not. Global symmetry should match for these two theories, but gauge symmetry is not like that. Gauge symmetry is not a physical; it's a redundancy. It's of course very, very important, but it does not determine the, I mean, physics. Okay. Okay. And this is okay. This is a duality. Which does not mean equivalent. Okay. So, could you speak again? This one. Okay, actually, yeah. Actually, maybe we will see that because of the two theories should match it. Actually, this is very difficult to find the Sabag dual, but Sabag found it. Yeah, how can he found this dual is consider the global symmetry of the theory, and what is the gauge singlet of the chiral superfield or something like that. Then they should be matched between the two theories up to this superpotential constraint. And also there is many symmetries, and also some it's called a two-foot matching condition. It's a symmetry with anomaly symmetry is also matched for the two theories. Then there is some only the option, not only the option, but he found that this theory can be equivalent to this superconformal field theory in electric theory. Yes, this one, this electric. Sorry, could you speak again? Yes, in some sense, but it's a yeah. But the gauge symmetry is a redundancy. So it's if it's a free, it becomes an infrared free theory, then here we can see this is like a theory with the SUNC because gluons, lighter particle is gluons. or something like that. But here, it's a superconformer. So its a coupling is non-zero. So we can not have a free, like a particle here, there. There's no notion of the particle in the superconformer 3. Okay. Yeah, it's just described by the gauge symmetry with gauge group gauge group NC. But it doesn't mean there is some glue on for the NC cross NC or something like that. So okay. So what they said is some correlator for the gauge invariant. Gauge invariant operator is only the gauge invariant operator is physical, and we can compute the correlator of the gauge invariant operator or gauge invariant state. Then this theory and this theory have a same correlator or same matter content or some same physical space at this fixed point. That is a claim. Okay. Okay, and okay. So this type of duality, is also not special. We can see such things in the 3D, 4D, 5D everywhere, because fixed point is very special. Actually, there is called the notion of the universality. Universality means the fixed point should be determined by the symmetry only. Symmetry means global symmetry. Okay, but maybe it's not true, but actually, at least fixed point is very, very special. So if it floats the non-trivial fixed point, then there is a huge fixed point. So sometimes two theories should have some same infrared theory. And for the supersymmetric gauge theory case, we can have a non-trivial fixed point, even in the 4D, 4D, 5D, somewhere. So then, sometimes two theories are cyberdual. That is the reason why, that phenomena, cyberdual type phenomena, can be seen for various supersymmetric field theories. Okay. Actually, field theory is very restrictive, and the supersymmetric case further restricted. Okay. Then, okay. So, from this cyberduality, we can flow this theory by adding a mass to the one of the flavors. Then we have a cyberdual for these region. this case, it's like this. And sorry. And so oh my gosh, どうしようかな。And we will define this NF minus NC as NC prime. Then okay. And here this is magnetic, and here is electric. And okay. So, okay, we will see this duality is forms duality at superconvoluted fixed point case. And here, gauge group is this one, NF minus 3 NC, and NF flavors QCD, but there is a NF squared gauge singlets. And the superpotential is like that, this combination. Actually, this is not renormalizable perturbatively, but this is a superpotential, and this is a relation between the scale, dynamical scale between the electric and magnetic. And okay, and this is a relation between the operator between these two. Here, electric is this operator is called magnetic meson, and this is called baryon, and this is a B Childer baryon. Another one. I didn't write down, but in the magnetic theory, there is a M here. This is singlet. So this one, of course, this has the same. Sorry, it's the same flavor charge, U1 charge, everything. And the baryon, for the baryon, we can construct a baryon operator for this magnetic theory. Also, it's we wrote it as B, small b. And it has NC prime indices because gauge group is now NC prime. Then, okay, this is not so good. I1 to INC, J1 to JNC prime. Okay. And this is a flavor indices. And this is contracted by this epsilon tensor. Here, epsilon tensor is, I learned from 1 to NF, okay? 1 to NF. So this has a NC, this number of indices is NC plus NC prime, okay? And NC prime is this one. So number of the indices is NF, okay? So then we have same flavor indices here and here, and we can check that these two operators have all same charges for all symmetry generator. Okay, but here maybe you think how about meson in this theory, like a QQ Childer, something like that. But here there is a superpotential. Then there is a gauge invariant operator is not independent because of the F-term equation, this vacuum equation. This gives this meson in magnetic theory is identically zero. Okay, it's not independent. Okay, then these two theories have a same matter, gauge invariant matter content. Okay, yeah. Uh-huh. This one. Yeah, okay, so here. No, this is a new M here. This one. There's a M, Q tilde, or something like that. From here, we can construct a Q. And there is a, of course, yeah, there is a little Q tilde here, but there is no corresponding one. Okay. Yeah, but but there is this relation. There is a superpotential in the magnetic theory. Then the magnetic theory, this operator is not independent. Okay. Then instead of this one, this singlet, gauge singlet here, gauge singlet is corresponding to this composite operator in electric theory. That is a claim. Okay. Sorry. Okay. Yeah. Yes. Sorry. Yeah. Okay. So let's take a break.
non ci credo. Veramente.
入ってるか。なんだっけ。Okay, so let's continue this. Okay, so to see, this is a correct result from this this conjectured superconfirmatory case. We add some mass term for one flavor only. Then, in an electric theory, it's in a low energy. These quarks decoupled because here we give a mass term, so in a low energy we cannot see this because of this has a mass. Okay, in a low energy we can forget about this one. Then the theory becomes SUNC NF minus 1 flavors. Okay. The magnetic theory this corresponds to the this one. Because this QQ chilled, this meson in original theory is mapped to this gauge singlet. Okay, so adding mass term correspond to the in the magnetic theory this linear term in superpotential. It's like a source to the theory. Then in a low energy, there is a source. So we should integrate this M, NF. Then we have a NF, and this is like a okay. So in a low energy, there's some relation like this one, but here QNF appears, so QNF also should be integrating out. Then, like this one, we have something, oh my god, like this one. And then there's this beta. So we will integrate on this one, then we have a QI, Q tilde NF equals 0. And also for replacing Q and interchanging Q and Q tilde, we have a similar relation. Okay. So then in low energy, there is such a constraint. Then solution for this is this. Okay. For solution for these equation, like this. Actually, this M is 0, so this 0, and because of this one, this is 0. Here we also take QI, this component of the QI equals 0, then this is 0, and this is also 0 because of this one. And this terms are proportional to M times mu tilde, something like that. Then we can cancel that. Okay. But anyway, in a low energy, these things happen. Then because of the Higgs effect, actually this have some VV because of this mass term, this source term. Gauge group becomes and the flavor becomes also -1 because this Q NF decoupled. Okay. And the remaining W superpotential is same, like sorry, here I J equal 1 to NF -1. Sorry. So this is the magnetic side. Okay. Okay, then sorry. Then original electric theory and the magnetic theory have two same infrared limit. And then we add a very, for example, very small mass term here. Then the remuneration group is deformed, but actually infrared theory is same. So it's some deformation. Sorry, some deformation of the infrared theory. So after the deformation, these two theories should have a same infrared limit. Okay. And but if we consider M is large case, then this should be something different root. And this different root is this one and this one. So then this by this deformation, we have another Seiberg dual from the original Seiberg duality, like that. Okay. So these two theories should have a same infrared limit. So these are Seiberg dual. So then we will see this one. This flow is consistent with this one. Okay. If the flavor is decreased one, then gauge groups NC and NC prime and NF decrease in the magnetic side. So then this is consistent because of the NC prime is NF minus NC. Okay. Okay, now so we have a series of superconformal field theory. Sorry. Series of Seiberg dual here. And okay. But then a magnetic dual theory becomes infrared free for this region. Beta function is the same as superKCD because just magnetic theory we have additional singlet, gauge singlet. So beta function is the same. So one beta function is 3 NC minus NC prime minus NF. So if this condition is satisfied, then magnetic theory is non-asymptotic free. So that means infrared free. Okay. So then that means so magnetic theory is infrared free. So we can see the gluon in this magnetic theory. Gauge group SUNC. Okay, so N equal 1 SUNC super QCD with NF flavor. Becomes free, non-abelian theory. So we see the non-trivial gauge theory flow to the free non-abelian gauge theories. Okay. The free non-abelian gauge theory is very strange things, but okay. But we should have that. Low energy limit is something very strange things. So, could you speak again? Uh-huh. Two flavors. Yeah, actually, yeah, it's yes, same, yeah, same as Mustang for one flavors, and then give a Mustang for another flavors. Yeah, yeah, and then yeah, like that we have these. Actually, the important thing is the superpotential. Everything is holomorphic, so there is no singularity-like structure or something like that. This is the underlying assumption for this flow in a supersymmetric Fourier theory. In a user non-Suji case, it's not like that. It's very complicated, but yeah. Okay. Okay, so this is like yeah, for the abelian theory, you want, for example, QED case, we know infrared theory is free electron and gauge boson, I mean photon theory. We can see photon and electron in the world. But we consider this one, we can see in a low energy something gluon and some quarks, dual quarks or something like that. And it's composite of the original SNC, like a baryon or meson in our world. Yeah, but it's a gauge, I mean, vector particle or something like that. So this is an example of emergent gauge symmetry in a low energy. And maybe it's very interesting if our world, like some material can have a non-abelian gauge symmetry as an emergent symmetry in a low energy. It's very interesting topics. But here for the supersymmetric one, some example of emergence of non-abelian symmetry, non-abelian gauge symmetry. Okay. And here I wrote this one. Actually, for these values, this argument is not valid. This case, so sorry, electric case is same, but magnetic one is now gauge group is SU2, and okay, because this is NF minus NC, so NC prime equal 2. So giving a mass term, because of the Higgs effect, so gauge group becomes SU1. That means gauge group is completely broken, Higgs phase. And this is SU1, and the superpotential is, but because of this completely breaking, there is some instant effect for the gauge symmetry. Because in a complete Higgs case, we can take the weak coupling limit, and then we will have an instant effect. And from the symmetry, we can determine the form of this instant effect. It becomes determinant M. Okay, so then and the superpotential becomes this one. So this is means here it's Higgs phase. Okay. Above that, gauge symmetry remains, so it becomes free magnetic. But here, gauge symmetry is completely broken, and this. And because of this is, yeah, we can say it's a confinement phase, but actually, because of the fundamental representation, matter have a quark, so it's a fundamental representation of the gauge group. So the confinement, in a strict sense of the confinement, can be defined by the area of the Wilson loop. Then, because of the fundamental representation matter, Wilson loop cannot be area row. So yes. So in a user sense of confinement means we can't have a gauge dependent particle in the world, like a quarks or gluons cannot be seen in our world. That is called sometimes a confinement. Then this Higgs phase is, in that sense, is a confinement phase. Okay. So it's in some sense, confinement. Okay. Okay, then we can add the mass to the this magnetic theory further. Then we have this region, and then this potential. And maybe we should see what is NF equal NC. That's the question. That's the question. But yeah, actually, yeah, maybe I will skip that. But we have some superpotential for the NF equal NC, and below that, this superpotential becomes same as what we got before. I mean, in the beginning of this lecture. Okay. So from this Seiberg dual, these things are explained, and of course it is consistent with holomorphic argument of the superpotential. Okay, so this is the phase diagram of the Unicorn super QCD from the holomorphy, and these are the exact results for that. And there are many strange things happen, like a Seiberg dual or something. Yeah, superconductor fixed point or Seiberg dual or free magnetic theory or everything. But okay, then I will skip this one. Oh. Or maybe so finally for the part 1 sector, before the introducing the localization technique, I will describe the N equal 2 supersymmetric Anomaly theory in 4D. This theory is interesting because it is called the Seiberg-Witten theory, and it is the AGT relation, Nekrasov partition function, and everything. It's very important theory, and I will introduce this one very quickly. But because of the time, maybe this is some review, but I'm not sure it's good or not. But so I will comment on the spectrum. Actually, I will explain what's the BP, the important notion of the central charge and the BPS state, something. Before that, I will explain n equal 1 supersymmetric case for the spectrum. Probably you know these things, but okay. Let us consider the spectrum of the theory. Okay, and spectrum, if the spectrum is massive case, massive means p0 squared minus I squared is greater than 0. That means massive. And then, in this case, Lorentz transformation can map pi equal 0. Then, p0 equal minus m. In this case, here we consider the operator formalism. And this is the Suji algebra for the n equal 1 case. Then we can define B alpha equal so then if we define this one, then yeah, this satisfies this algebra. And this is equivalent to two free fermion. This one. Then irreducible representation of this algebra is this one. Okay. Now, of course, this structure will be squared 0, b dagger squared 0. So this is like this. Okay. Here, this case is a scalar particle case. Then the two scalars and two fermions. Okay. Okay, B is a Fermi operator. So these two, B1 dagger, B2 dagger, these two are scalar and these two are fermion. And the spin of this one is a spin 0 times 2. So two spin 0 states, and these two becomes spin pair. Yeah, spin 1/2, archer 1/2. A half state. Okay, and if this is a spinner, case, it becomes a 4 fermion. 4 bosons, because alpha can take 1 and 2. It's a spinner. Then there is a two spin half representation, and one spin 0 and one spin 1 state. Spin 1 state describes a massive gauge boson. Okay, this is the case of the massive case. And if consider spin 2 over 3, sorry, 3 over 2 case, this case should be supergravity. Because in this case, this contains always a spin 2. Actually, it's massive gravity, but anyway. So massless case. Then this case, by the Lorentz transformation, we can make this choice. Then, because of this, because of Suji algebra, this Q1 dot anti-commutator becomes 2m, but Q2 bar becomes 0 because of the Pauli matrix. Okay, then, sorry. In general, for in general, if we have such a operator with constant c, then we can take VB for the any state. Then we have such things, and this should be positive, or I mean non-negative. Sorry. So C should be non-negative, and also if C equals 0, then R itself is 0. Okay, then this case, applying this one to this one, then Q2. This Q2 should be 0. I mean, represented by 0 for this massless state. Then, so there's only two states. So compared with massive case, only there's only I mean half the number of states appears for the massless case. Okay, this is for the n equal 1 case, and we can next we will generalize this one to the n equal 2 case, especially n equal 2 with massive case. Then such a half number of states appears. It's called a BPS state, but yeah, our time is already over, so I stopped here. Sorry.